So welcome back, NCEA Level 1 physicists and earth space scientists, continuing on with the energy external standard. Today looking at the sources of electrical energy. And we've already looked at a few examples of it, at least one example, the battery. Okay, so the battery is one source of electrical energy in a circuit. So when we're looking at a circuit, we really haven't answered what causes the current, what causes those electrons to flow. Okay, so the voltage, another name for that, is the electromotive force, but it's not actually a force. It's the energy per unit charge, okay, so energy in joules per electron, imparted by an energy source like the battery, the chemical reactions in the battery. So what happens is there's chemical reactions inside the battery. They create that potential difference we looked at in the last lesson, which then does work. So again, applies a force over a distance, as you can see from the image here, on the electrons through the circuit, causing the electrons to move. And we call that moving of the electrons actually electrical energy. So the voltage really, in simple terms, provides the oomph or the pressure, if you're using a water analogy, for the electrons to move. So in terms of recharging batteries or rechargeable batteries, what happens is they actually have a chemical reaction which reverses the polarity, okay, that produces a potential difference by then passing a current through the battery in the opposite direction that it would normally travel, therefore allowing the battery to be recharged, as it were. The reaction going forward is then occurs again, and electrons can flow due to the voltage being formed. So voltage isn't constant over a battery's lifetime. So as we saw with the rechargeable batteries, eventually that chemical reaction stops happening, and over time the voltage or the energy provided per electron reduces down until eventually, over time, it goes down to zero. That's what we call a flat battery. Now, batteries are not the only source of electrical energy. The supply voltage of a circuit basically puts the energy into the circuit. We've already seen that. And so the electrical energy can be provided by batteries, which we've already done, but it can also be provided by generators. And so electrical generators, basically what happens there is you have kinetic energy, say from a turbine in a dam, or a wind turbine, or even a combustion engine, or other ways that a turbine can move. That then generates electricity in the generator, which then drives the electrons in the circuit to form that current to allow electrical energy to begin to flow. Another example, apart from generators, is solar panels, which we have lots of in Marlborough. So in terms of energy, let's go back to the LOL diagrams. So now we're introducing the concept of electrical energy. So if you think about a kettle, the system's going to be the kettle and water. The water in the kettle to begin with is cold. It requires energy in order to increase its thermal energy, and that gets the energy from the electrical energy, which is now being put into the system. So that means that the temperature of the thermal energy increases, so the cup of tea, as it were, or the boiling water gets hotter. But you can see that the initial state is going to be 2 plus 3 in total, because you're getting 3 units, as it were, of energy from the electrical energy from the main supply through the kettle. And at the end, you have 5 units of energy, of thermal energy. So energy is still conserved. Okay, so energy conservation still exists. And then for a wind turbine example, generating that electricity. So now the system is the turbine and the wind. So the initial state is the turbine spinning. The final state is still the turbine spinning. But you'll see there that the kinetic energy of the air is being transferred into the kinetic energy of the turbine. And the difference leaves the system as electrical energy for the main supply. So it's actually generated electrical energy. Okay, so again, in the beginning you have 4 plus 3 when you combine the kinetic energy of the air and the turbine, and you have 2 plus 3 of the kinetic energy of the air and the turbine again, and 2 units of energy is being taken out of the system. So again, energy is still conserved, and you'll notice also that the kinetic energy of the air goes down because the airspeed slows slightly down when it interacts with the turbine, which makes sense.